Thank you. So we said that there are quantities in this equation that need to be determined, and we spoke briefly, at least, about the thermodynamics. Next, we want to talk about the transport equation, so the transport quantity. So the next one is diffusion. Now, if you have a mixture which is only involved two components, then there is a known law which is known as Fick's law. Fick's law, as I said, of binary diffusion, which says that diffusion flux, right, which is rho times rho 1, if you like, V1, or rho yi V1. So the flux is proportional to the gradient of the concentration of that species. And the same you write for 1 and the same for 2. And since the sum of yi, y1, y2 is 1, then the gradient are related. And since the other constraint that y1, v1 plus y2, v2 is 0, then those are connected. So it's easy to deduce that there is only one diffusion coefficient. The diffusion, which is denoted here by d, 1 into 2 and 2 into 1 is the same. And so you can write the Fick's law as rho yi vi is minus the mass diffusivity, or well, d is the mass diffusivity, which is in unit of centimeters squared per second, like any other diffusivities. So very often rho times d is referred to as the coefficient of diffusion. So it's a matter of notation or what you refer to, but this is clearly a diffusivity. Now, when you introduce this in the species equation, you get, of course, the idea is to eliminate the diffusion velocity, and you get a species equation or a diffusion equation as such. When rho d is a constant, it gets pulled out and you get the Laplacian. And this is, Fick's law is very similar to Fourier law of heat conduction, but instead of that the heat is transferred due to temperature differences, here mass is transferred due to concentration differences. Now, but what happens if you have many species? So really the multi-component diffusion in gases was first expressed or given in Hirschfelder, Curtis, and Bird, and it's written in that form. It's a very lengthy form, so let's just point out a little bit what it involved. So first of all, it's not written as Fick's law that the diffusion velocity is equal, but it's related in an implicit way. In other words, the diffusion velocity are related to the mole fraction, xi, in that form. And so there is the difference in diffusion velocity produce a gradient in concentration, but also the gradient in pressure affect that, and also the gradient in temperature effect, which is often known as the Soré effect, is also produce a gradient in concentration, and even the difference between body forces produce a concentration in concentration xi. Now, some of these things are relatively weak or small. So for example, the Soré effect is usually neglected. The pressure gradient also are usually neglected in using or in determining the diffusion velocity. The body forces, again, it depends if you have some ions or electron, as I mentioned before, and they have different Fi, so this may play some role sometimes. But if these are all neglected, then what is left is what is typically used as and known as the Stefan-Maxwell relation. And these are the Stefan-Maxwell relation. Again, it tells you that if you know the mole fraction, or the mole fraction, you will know the diffusion velocity. Note that for a species I, it's related to all the other species. And the Dij are also diffusivities, in other words, have units of centimeters squared per second. And there's some argument that can be proven that they are symmetric. In other words, Dij and Dji are the same. So this is perhaps one of the simpler form of the multi-component diffusion, which is often used. But even this is complicated. First of all, it's an implicit relation. In other words, we don't have, like we had before in the Fick's law, that we knew what VI is, we plug it in the equation, and we have an equation for the mass fraction. It's an implicit relation here. And then, you know, it's not, oops. It's a complicated relation by itself because it depends on all the species I. So very often there are some simplification used. But the first comment is if you use a Stefan-Maxwell relation for two species, you can recover Fick's law. So there is a consistency here. The second thing is that sometimes it's convenient to write, as I just mentioned before, an explicit relation. In other words, VI is equal to something, okay? The problem is that if you write an equation like this instead of the Stefan-Maxwell relation, which is often known as generalized Fick's, okay? It's, the Dij are not simple experimentally determined quantities. In fact, they depend on concentration, and so it's not a very convenient way to do, but for computation, it may be easier. Another useful approximation that's often used is what's called an effective binary diffusivity. So what you do is for the diffusion of species I in the mixture is obtained by writing an expression similar to Fick's law, but in terms of concentration as xivi with the effective value. And the effective value is obtained by assuming that all the diffusion velocity of all the other species is 0. So if you substitute that idea into Stefan-Maxwell relation, you obtain what the effective diffusivity is. So you can compute it this way and use a simple law, basically. We are going to use in the discussion this week a simpler version because we are not going to deal with very complex chemistry, but only with simple global reaction. And we're going to use what is often referred to as a dilute mixture. Now, I go through here some steps because it's very important when you have some, when you make some assumption or simplification, and when you get the result, that you interpret the result based on the assumption that you have made and not otherwise, because otherwise you're not explaining the correct thing. So you will see where that comes into play. So for example, the dilute mixture means that the combustible species of interest are usually in small amount relative to some bulk. So very often when combustion in air, then nitrogen is a bulk, and so you can assume that the other species are small quantities. What does it imply? It implies essentially that the molecular weight of the mixture is that of the abundant species, say nitrogen, Wn, that all the yi except for the n are small, and so that when you substitute that in the Stefan-Maxwell relation, and I know I'm rushing here because time, you end up with a simple fixed type relation, okay? You see the diffusion flux is proportional to the gradient of the mass fraction yi. But what is this di? What is this diffusivity? Is diffusivity of species I into the bulk. And that's how you have to interpret it when you get the result. So, so we can write now, instead of the complex Maxwell-Stefan relation, a relation like this, which as for a binary mixture, I can plug this into the species equation, which I will do in a minute, and get a simple relation for that. And remember again, the di, even though I didn't write here the capital N, it's meant to be din, namely the diffusion of species I into the bulk. Okay, so, oh, I have here a pointer. So now when you, again, plug this in the diffusion term, you get a simple equation for the, for the mass of species I, which is in the form of rho times dy I dt, the time rate of change of the mass fraction is due to diffusion and chemical reaction. And again, those equations, there are only n-1 independent relation, because always the sum of the yi is equal to 1. So numerically or mathematically or whatever, when you use this equation, you can only use n-1 of them. Or if you use all of them, this is a validation, whatever you do. It's, by the way, it's, actually it's not quite accurate what I just said. You don't want to use all the n1 because the di was defined as the diffusion of species I into the bulk. Now, to write a similar equation from the Stefan-Maxwell relation for species n, it would involve all the species. So you want to avoid that one and use the sum of all yi is 1. Okay, so this is about the species equation. The next thing is the heat flux. Now, the heat flux term here depends not only on the Fourier law as for a pure substance, which is the gradient of T times the conductivity of the mixture, which is, again, a property that has to be defined as an average of all the conductivity of the species. But also it depends on the diffusion velocity. Due to diffusion, there is some heat transfer because different species have different enthalpies, HI. And this is the second term in this expression. And then there is a term which is somehow equivalent to the Soré effect, which is known as a Dufour, and typically it's small and negligible. Basically, it says that you can also difference in the diffusion velocities can produce also heat. Usually that term is negligible. If you are interested also in radiant heat flux, you have to add to the Q that component. I will add it only when necessary, usually not often, actually never. Okay, so in my discussion, I mean never, not. Okay, so the energy equation now in terms of the internal energy can be written as such. These terms are quite familiar. As before, the work, the viscous heating or dissipation function, the heat flux, but the heat flux has the heat flux, and then remember that term. This is a copy from an equation I derived earlier, or I discussed earlier. And when you substitute for Q the first two terms, neglecting the Dufour term, here is the first one, here is the second one. So there are some terms here that need to be still discussed or perhaps simplified in some way. So the next thing is to, okay, for simplicity of presentation, I will only keep the body force gravity, so this term is gone, okay? Because if there is G here for all the species, yi vi is equal to 0, and so that term is gone. It's always, the gravity term never appears in the energy equation, always appears in the momentum equation. Okay, so the next step is to discuss this term here that we have. And so there are two ways to approach this, and I'm going to go through this very quickly, only a few words. One of them is you replace the enthalpy by the sum of yi hi, and you express that in terms of the enthalpy of formation, Hi0, subscript 0, and the CPI. The second version is to replace this with Yi Hi naught, the integral of the mixture-specific heat, okay? And in doing one or the other and some manipulation, you end up with one of those two relations. Note that the first one is expressed directly in terms of the temperature, okay? Those all the terms as before. This term is due to the diffusion fluxes, the heat fluxes. And note that the last term, which is related to the, as we will see more specifically, to the heat of combustion, is expressed as the enthalpy of species I times the molecular weight of species I. The second version involves here the integral of Cp, which is for the Cp of the mixture. And that term is a little different here because of that use of H. But the last term is the enthalpy of formation multiplied by omega I. The difference is that this one needs to be computed for each I, whereas this one, as we'll see later, is a constant times omega I. So clearly for computation, it doesn't matter which one you use. It depends on, I guess, what is available to you. But in theory, it would be easier to use the second one, as you will see. Now, before we even go into that, I want to mention that, in fact, we are going to assume later on that all the CPI are very close to each other and are almost constant, or replace them by some average value, the Cp, and therefore this term actually, whichever equation you want to use, give you the same end result. The reason is that this term, when all the CPI are the same, it's going to go away because that integral wouldn't have an I, and then rho yi vi is 0. And for the same reason, after you do whatever manipulation, this term will go. And then this one will end up as the enthalpy of formation. So anyway, so this is the equation that we want to focus on, which is an equation that, it's an energy equation, depends on the temperature, heat conduction, the work done. Remember, oops. No, there is a mistake here. Just a second, let me. No, that's fine. So right, this originated from the enthalpy equation, and that's why what you have here is dt dt and dp dt. If it originates from the internal energy, it has a different form. And then the viscous heating and the term that come from the reaction that we will discuss later in more detail once we talk about chemical kinetics. Okay, so we end up now, it's a summary of the equation. So we have mass conservation for the total mixture, mass conservation, if you like, or balance equation of the mass of the different species, yi, and we use n-1 of them, where the di, as I explained, is the binary diffusion of I into the bulk. The momentum equation, and I left only gravity here. Even there, we will use it only rarely. And then the energy equation, as I just showed you a minute ago. And then the equation of state, which we have derived early on when we assumed that all the species all the species behave like ideal gases. Okay, now if we know the omega I, which is the rate of production, destruction of species I from chemical kinetics, then we have n plus 5 variables Rho is 1, yi is n minus 1, so it's n plus 1 plus 2, and 3 more plus 5. So we have n plus 5 equation to solve, and we have also n plus 5 variable to solve for, and we also have n plus 5 equation, 1, n minus 1, so it's n plus 3 plus 4 plus 5. Okay? So again, we have a system which is mathematically consistent, or it's complete. The coefficient lambda mu di are mixture dependent in general, but usually they depend primarily on temperature, and I'm going to go through that actually very quickly. They each have typically the range of the diffusivity is depend primarily on temperature, not so much on pressure, and the coefficient is typically between 3.5 to 2. The viscosity is also behaves similarly with a coefficient between 3.5 to 2. This is based all on experimental data or measurement data. The thermal conductivity go like T between half and 1. Typically it's 0.7, but anyway, it's in that range. And so the diffusivity, which is the thermal diffusivity, is again between 3.5 to 2. So note that the mass diffusivity, viscous diffusivity, and mass diffusivity, viscous diffusivity, and the thermal diffusivity all have very similar temperature dependence, and so the ratio, which are known as Lewis number, Prandtl number, and Schmidt number, are more or less constant, okay? Because they are a ratio of things that depend on temperature, but approximately in the same range. And very often they are used as such, and even if you want to, so if you want to retain some of the temperature dependence of this coefficient, you can always write for the mass diffusion, you can write it as lambda over Cp multiplied by the inverse of the Lewis number. Lewis number is the ratio of the thermal diffusivity to the mass diffusivity. And since this is a constant, then it depends on lambda. The same thing with mu, you can write it in terms of Prandtl number essentially multiplied by lambda. And so if the Prandtl number is about constant mu, they all have one, so to speak, temperature dependence. Okay. And there's a source here where you can find, those dependencies. Anyway, this is was supposed to be the end of the previous lecture, so let's move on to lecture number 2. And here we want to briefly talk about chemical kinetics. This is not a course on chemical kinetics. Oh, before that, I have moved certain things from the order of the lecture. Those notes appear at the end of lecture 2. I moved it to the beginning, but I will get to the, I'll just change the order. Again, I want to be brief on this because of time. Let me put this on a play mode. So I want to talk briefly about the conservation equation at an interface. This comes into play in different ways, as I will actually mention as I go along. So suppose that we have an interface which is shown here in red, and I want to express the conservation of mass momentum energy across that interface, or if you like, the difference between the values on the interface to the left and the right. So what we do is what we call a pillbox argument, which is we create a control volume which enclose the interface. What you see is here is blue. And we write the governing equation in that box, the equation we wrote before, because they're valid everywhere, they're valid in that volume as well. And we integrate them from one side to the other, assuming that the thickness of that box, which is h, goes to 0. And then we obtain a relation on the left, on the bottom or left, that relate to the values on the top. And so I will skip the details, but essentially when you go through the conservation equation we did before, and we do that, and I'm going to skip as I said, for mass conservation you get a relation as such. They are all denoted as jumps. So you see here, you can see the exact integration. You have a quantity which is in the volume, and then you have a quantity on the surface, the bottom and on the top, or on the top minus the bottom. The plus meaning the value on top, the minus the bottom. And so if you assume that there is no accumulation within that volume, then essentially what it tells you, the mass flux in is the mass flux out, okay, which is a conservation of mass. So this notation that I will keep occasionally in these lectures is a jump, one side minus the other. As long as it's equal to 0, it doesn't matter if it's left minus right or right minus left. When it's not equal to 0, I will be consistent and I will tell you what I mean by that. So this is a conservation of mass. We can do the same thing for the different species, but here we have to assume that there is also no chemical reaction created at the surface, so on the surface. If there is, then what you do, you express the chemical reaction rate as a surface rate multiplied by a delta function, and when you take the limit, it's the surface rate enter into the play, okay? That will be relevant, for example, if you want to determine the condition at the surface of a particle that is chemically active on the surface, okay? And then the conservation law will be given here, where this omega I is the surface rate, reaction rate. Okay, so this is the second one, and we can do the same thing for the momentum equation and for the energy equation. I just wrote them here. Now, if you, let's focus on the momentum equation, for example. So you see that's a vector equation, right? And so it has 3 components. So when you have an interface, it's natural to decompose them not in x, y, z, but normal to the interface and tangential to the interface. So when you do that, for the normal component, you're going to dot this with n. So you're going to have a pressure n dot n is 1, and then whatever remain here from the normal side, and then the other thing from the, again, I'm not showing you the details, but if you neglect viscous forces, then what you get are these 2 relations. The first one comes as the normal component, which tells you that the jump in the pressure plus this is the mass flux times the normal velocity, okay? So essentially is the momentum in the normal direction is conserved, okay? And the second one tells you that the tangential component are conserved. In other words, there is no jump on the tangential component below and above are the same across the interface. And those are known as Rankine-Hugoniot conditions. They are essentially simple conservation of mass and momentum across an interface. They are used, for example, in shock waves. They will be used or can be used if you treat a flame as an interface because you want to conserve mass and momentum and energy, and that's the proper relation that do that. Well, I put that, I added this on, but just to tell you that the same relation gives you also condition usually across an interface between two liquids, so a solid and a liquid. That's how these relations are derived. For example, if you look at a spherical bubble, then there is no surface shear between, so that's 0. And as a consequence, you get what is known as Laplace's relation, which tells you that the difference in pressure is related to a coefficient, which is denoted here by gamma, multiplied by the curvature, 2 over r, which is the curvature of the sphere. So you see, this relation are useful in this context in different, different application. It's also useful in some of the lectures that I will follow. For example, when we want to determine the condition at the surface as the boundary condition, say, on the surface of a droplet, say. The droplet is evaporating, so the liquid is leaving as gas, and you can write the jump in the mass flux as you see here, because the assumption is that the liquid is not in motion, so V is 0. And so the only thing is VI, which is the rate that the surface is moving. And that's related to the flux of a gas that is leaving on the other side. So this is expressed essentially from these jumps. And then if you assume that the rate that the droplet recedes is slow, you can obtain this relation, which I will talk in one of the lectures later on. You can also obtain what is the proper boundary condition on the surface of the droplet for the species, for example. Again, under natural assumptions such as there is no motion in the liquid, and also diffusion in liquid is very small usually, it's not like in gases, then you can obtain, and if you use Fick's law, then you can obtain the relation that you see here. Again, they are derived from those jump relations. This relation simply states that the total flux of the fuel, convective and diffusive, is related to the velocity v, or to essentially the rate that the droplet is, well, v is the gas velocity here it's leaving. And since there is no oxidizer inside the droplet, then the total flux is 0. So anyway, I just wanted to point out that this conservation equation can be used also to derive more appropriate equation across interfaces, and that's the main point of this discussion. But I will, and similarly for the energy equation across the droplet, I will discuss that when we talk about droplet combustion, so I'm going to skip it here. So again, we go back to this same equation, and the only thing that we want to discuss now is omega I, the reaction rates. Okay, for this we need a brief discussion of chemical kinetics. So if we have different species that I refer to as the script Mi, for example, different species like H2, O2, CH4, and so on, a chemical reaction can be written mathematically in this form. Nu I prime Mi goes to nu I double prime Mi. Be careful that in this notation, I is all the species, okay? The prime indicate the reactant, so it's equal to 0 if I is not a reactant, okay? And the double prime indicate things on the right, so it's 0 if it's not a product, okay? So for example, for H2 plus O2 goes to 2OH. There are 3 species. I denoted H2 by 1, O2 by 2, OH by 3. And you can see that nu 1 prime and nu 2 prime are both 1, and the double prime is 0. And nu 3 prime is 0, but double prime is 2. Okay, and then there is, of course, a relation between the molar production or consumption of species to each other. Because in that reaction, for example, you need 1 and 1 to produce 2. So the change in number of moles of OH divided by 2, the change in number of moles of H2 divided by 1 and O2 divided by 1 are the same, which you can express in general in this form. dNi divided by the change in the stoichiometric ratio is equal to dnj divided by j double prime, j prime for any pair I and j, okay? Which we can express which we can also express in terms of the time rate of change of the concentration, dci dt, which is essentially the rate of production or consumption. The reason for the hat, it's because I use this for mole per unit volume, whereas if you remember in the governing equation that we derived, we wrote everything in terms of mass. So omega I without the hat is mass per unit volume per second, whereas with the hat is. So the difference will be bringing in the molecular weight, as we will see in a minute. But anyway, those are all related for two species, I and J, and therefore they are all equal to something that omega, that we refer to as the reaction rate, a mole per unit volume per second, and it's independent of any I, okay? In fact, the reaction rate is the consumption of species where the difference is 1, okay? It's just an obvious observation. So as I said, if I want to write it in terms of mass per unit volume per second, I would have to multiply by the molecular weight. So omega I that will enter into our governing equation is the difference in the stoichiometric coefficient, molecular weight times the reaction rate, and we will discuss what the reaction rate is in a few minutes. Before we do this, if we sum all the omega I, we just get omega times the sum of this. By definition, this is equal to 0 because this is essentially the chemical reaction that we wrote multiplied by the molecular weight of each species, okay? So that's just a consistency condition. I put here an example, which you can look at it later, but just wanted to quickly mention that, of course, in reality, the chemical reaction of methane or the oxidation of methane doesn't go in a simple way as this reaction. There are many steps going on, many intermediate species that are created and destroyed and so on. And this is all a discussion for chemists, and as well as there is a big activity of how you really simplify such system. I think I made some comment about this in one of the next slides, but let's move on until we get to there. We are missing the reaction rate, okay? Omega. So again, we rely on a phenomenological law. In other words, a law which was obtained by experimental observation. And that's the law of mass action. What it says is that the reaction rate is proportional to the concentration of all the reactants. Now, if y is raised to nu I prime, because if you have, let's say, 2H2 in the reactant, there are 2, so it's H twice, and so you raise it twice, essentially. Okay, so this is the law of mass action, and the proportionality coefficient is known as the reaction rate constant, even though it's not a constant, it depends on temperature, but chemists always obtain these quantities using under isothermal condition, and so that's why it's referred to as a constant. But it's tabulated, and it's going to be found. Oh, I'm sorry. There is still some discussion about that, which will come in few minutes. So the law of mass action appropriately represents the process that occur at the molecular level and would be applicable only to elementary reaction. So it's not necessarily true for a global reaction, but nevertheless, we use it for a global reaction, but relax the idea that those are the stoichiometric coefficients. So they can be just empirical number that we refer to as reaction order. So it can be a reaction order with respect to the fuel, reaction order with respect to the oxidizer, or an overall reaction order, which is the sum of the reaction orders. I think I mentioned that later on. So what about the reaction rate constant K? The idea is that it depends on, we use the dependence on temperature is through an Arrhenius law, which states essentially that it's proportional to the exponential of minus E over RT, is known as the activation energy, as is the gas constant. And there is a weak temperature dependency here, which is often neglected, but it's written as T to some alpha. And the origin of this expression is the probability that two molecules will collide to create a chemical reaction, and for that they have to be aligned in the right direction and have the right amount of energy, and so you need to overpass this activation energy for the reactant to interact and produce the product. Anyway, the idea is just to write that equation to tell you where it comes from. So at the end, the reaction rate is the reaction constant, E to the Arrhenius part, and the concentration raised to the nu I prime. But I didn't say yet that for I said already that for a global reaction, we're going to relax this. This is going to come probably soon. When you have many reactions, you have to write such an equation for each of the reaction. Since I'm not going to deal with this, I'm going to skip that. And some of the most important question in chemical kinetics is to determine, first of all, for a given oxidation, what are the elementary reactions that are involved, and the two, to determine the specific rate for each steps. And there is all kind of information about this. And of course, there's also an attempt to reduce the number of such reaction, and it's often referred to as model reduction or simplified reaction mechanism. How is it done? Well, there are few ideas. I'm just listing to you what is done in the literature, not that I will address. The first thing is intuition and experience. A lot of intuition is put in to determine those rates. The second, there is something which is called sensitivity analysis, which what you do is you produce a small perturbation in the parameter and you see how that affects the system. And if it doesn't affect much, then you assume that it's not an important step. And then there are steady state and partial equilibrium approximation, which are more, those are some of the old ideas, which are more analytical way to simplify some of these steps, basically by saying that some species don't live long in the system, and so you can assume the time rate of change is almost zero. And so that reduces the rates into some simple algebraic relations, so you have less. And then there are computational methodology like ILDM, which is known as intrinsic low dimensional manifold, computation singular perturbation. different icons. They all have different idea how to simplify the system, but all of them involve some kind of approximation. So for example, just roughly speaking, when you say about the ILDM, what they try to do is separate between the very fast and the slow reaction. But how do you determine fast and slow? There's an input here that, as a researcher, you say 0.001 is slow, and so on. So there's always, it's not an accurate, it's not a precise, it's one that involves modeling, and that's the difference. Okay, so we are going to use mostly a global reaction, but so we talk about a global reaction, for example, of this form, and as I said that already, so what we are going to do, we allow for the reaction order to be some empirical number, not necessarily associated with the stoichiometric coefficient, and the sum of all the Ni is n, the overall reaction order. But you have to be careful that is done only in the law of mass action, but not in the relation between omega I to omega. That depends on the actual quantities that enter into the reaction, and so this are the exact stoichiometry that you will find here. For example, for CH4 is 1, the double prime is 0, and so on. So the reaction rate is therefore now, we have an expression for it that depends on physical quantities like temperature, mass fraction. So again, it closes the system of equation. This is just to show you that there have been attempts in the literature of determining reaction order, which here are denoted by A and B from that reference, Westbrook and Dreyer. And what I want to point out, and the reason for I put that, it's because now the A and B don't have to be integers like stoichiometric coefficient. They can be fraction, they can be even negative in some situation, okay? And the way they try to obtain those was just to match some fundamental quantities like laminar flame speed or flammability limit and so on to such a formula. In other words, it's a model of the real system. Okay. In the conservation equation, if we write the omega I, then the equation becomes on the right here, nu I double prime minus nu I prime molecular weight times omega, and we have an expression for omega. And the next place where it appears in the energy equation. Remember this term. Now, when you replace here the omega I with exactly this term here, nu I double prime minus prime wi multiplied by hi naught, multiplied by omega, which doesn't have an I. So this quantity is a constant, which is the difference between the enthalpy of formation of the reactant over that of the product, and this is known as the heat release or the heat of combustion. And so the minus the change in enthalpy is the heat Q, which is a positive quantity in combustion, and that's the notation I will be using. And so my energy equation now is here. All these terms like before with Q times omega and omega known from above. Okay, so for a two-reactant mixture that we will often use, then this equation will be, I will be either fuel or oxidizer, and then I only kept the nu I prime. In fact, I don't even need the I can call it nu F because it's 0 on the product end. The product is obtained from this relation, it's the energy equation and the concentration, the reaction rate with the NF and NO general. Okay, so now just a few comments about stoichiometry, and then I'm going to take a break. Well, we went beyond the time. Okay, you know what? Let's take a break now and let's try 10 minutes, and then we'll come back. I want to finish on time so you can go to lunch. So.